started. So today we're going to be going through the unconditional mean calculation that we started with last time. We worked out this. So under just observing one data point, and so just imagine that's all you get to see, just one data point. And you use these improper, but more importantly, kind of pseudo-optimal priors. I say pseudo-optimal because I haven't told you what optimal means yet. And so these can be derived under some optimal conditions. Turns out these are reference priors. These are Jeffreys. They have transformation and variance. And at least one-dimensionally, they optimally cover. Now, you don't just get that for free out of any old set of priors. And Bayesians would love to have a framework for here's the prior that gives you optimal coverage. I did say for a previous example, under the beta half-half binomial thing, we got optimal coverage. Larry Brown, when he proved that, had to do a bunch of math to show that you really couldn't do better than him. And so these are pretty good choices. Most people go after them and can derive them. We kind of used our intuition to come up with them. It turns out they're hard invariant under scale and shift, respectively. So lots of good stuff. We came up with this answer right here for our posterior. Our posterior is this thing. Mu can vary between negative infinity and infinity. So this is a distribution on mu. We get that by looking over here. Let's fix the thing on the right-hand side. So x was observed. And this thing was improper. And I said last time, this is a horrible answer. And I would say from a practical standpoint, it is a terrible answer. From kind of an analytical standpoint, my mind tells me this is actually a really good answer in some ways. Remember, the likelihood looks like this. The likelihood over phi and mu given my data point. This is just going to be proportional to phi 1/2 e to the minus x minus mu phi divided by 2. So that's my likelihood function over both those parameters. And it turns out, if you try to integrate this over mu and phi, it'll blow up on you. There's not enough information in that one data point to pull the tails down in that likelihood. In this penalty right here, which is a pretty mild penalty, there is some form of penalization here. Now on a linear scale, there's no penalization on the mu's. There's not enough penalization to bring down the tails of that distribution. Now I say it's kind of a good answer because there's not enough information in the system to simultaneously infer those parameters. You should not be answering the question. You know, you've given me one data point. Whatever I'm going to get, if we changed our priors and we put more penalty here, and we looked at our posterior variance, it would look a lot like our prior variance. For posterior, it looked too much like our prior. That means we're injecting all the information through our prior. If we change our prior and make this thing proper. I think from a mathematical standpoint and an inference standpoint, this is an answer you wouldn't deliver this answer. However, from a mathematical standpoint and from a statistician's viewpoint, this is a good answer. It's telling you you don't have enough information in the system. And I've had this happen to me in more difficult cases where I build some model and I start slapping some priors around and my MCMC doesn't converge. You'll understand what all that means soon. I can't figure out what the posterior is computationally. I can't draw from it. I can't do anything with it. And upon inspection, I figure out that my posterior is improper. That means that my model's no good to infer the parameters given the data set that I have. It might tell me I need more data, but it might tell me I need better model. So to resolve all the parameters. And so sometimes the solution is get the right joint prior, and sometimes the solution is get more data. And so I kind of like, this was the first time in many years that somebody said, well, right after, I think Ben said, change prior. I know what I can do mathematically, and then he switched gears and said, how about more data? And that's a really good answer. Go get more data. And so I have done an analysis that's in print, and it uses 3 data points. And it's a vector, you know? And it's like, how much information is there in those 3 data points? You might say ridiculous. I would say the analysis was highly model-driven. So our assumptions about modeling dynamics were heavily influencing our solutions. But I think 3 data points is a lot more information than 2. And 2 is a lot more than 1. And so imagine you saw something like this. This is supposed to represent minus infinity to infinity. So infinity way out there, minus infinity way out here. So this is a big, vast land. And let's say I sampled an x from some normal distribution, and I got this. I'm kind of inclined to think, I don't know, I think that it's centered around here. But I really don't have any idea what the variability is. And so this could have occurred in this place because of the stochasticity in the system, the variability, or because the distribution is very concentrated in this point. And I have no idea which one is true. And so, and I'm unwilling to say jointly what I think mu n phi is, or sigma squared. Well, let's say I drew one more time, and I got this right here. I would be astonished, you know, if it's like, wow, it got really close. What are the chances? And in statistics, you start to think, I don't really believe in coincidences. I quantify my uncertainties, you know, and so it's a different mindset, but it's like, why would that have happened? Either the mean is right here and I just got really lucky and there's a lot of variability, or there's not very much variability in the system. I'd be inclined to think there's not a lot of variability in the system. If all of a sudden I saw a third point in that area, I would be very convinced. And so just from a human standpoint, it's like, I see things 3 times and it's like, you know, I'm no fool, I know what's happening next time. And so, you know, some people take that logic to the casino and they do roulette and they see 3 blacks and that's a fallacy. That's not the exact same reasoning because you've got all the probabilities worked out for you. And so, but I think 2 data points and 3 data points kind of have a lot of information in it. So if the data points were really spread out far from each other, I'd be like, pretty noisy system, we're going to need more data. So I think the answer here is, let's go get some more data and try to do this analysis right. After we finish this answer, we're going to move on to this problem right here, inferring phi. I'm not going to do the whole thing for you. When you don't get to see mu and you don't have knowledge of mu, you're going to do it on your homework, and then we're going to get into predictive distributions. There's lots of stuff coming up. If you're worried that we're going too fast, I'm going to repeat all of this and just change the distributions on you so we get one more week of practice on what a Bayesian does. And then that's basically it. We can get into fancy things and issues and, you know, more mathematical descriptions of everything we've already kind of conjured up.
We're talking about the next homework, right?
That's right. My next and your next might not be the same next. So always check with people when they say next. So mine is always the one after this one. So this one is the upcoming one.
Yeah.
So be careful when you've had this one before. I've had it. I have it all the time. Somebody says next. So, okay. We want to derive. So our goal is going to be to find pi phi, the posterior distribution. Sorry about that. Mu, given a whole bunch of data. We'll say this data is x1 to xn, where these xi's are iib instances from this distribution. So sigma squared, I like to think about phi. So when I talk about one parameter, I'm talking about the other one as well. And so we're just going to collect more data. We're going to use the same primitives. We want our posterior. We know what the likelihood function is because you've told me the sampling mechanism. Tell me the sampling mechanism, I know what the likelihood function is.
Wait, real quick, so the mu in the second line is like a mu naught? Or it's not the same mu, right?
This right here is the sampling.
Oh, gotcha.
So what I'm going to do is I'm going to collect n of those data points. So I'm telling you the sampling mechanism.
Is that the same mu as volume mu or is that?
Yeah, that's right. So I'm generating data with this mu. This is true mu right here, and this is the space in which mu's live. And so this is a number that I plug into this. And if you wanted to write this down very professionally, you would say this right here lives in some space, and you would define the space, and then you would define the realizations of these, and we can use these to estimate that in quantified inserts if you got it. And so I'm recycling all the notation. But it is the same mu that we're estimating. So this is a posterior probability on mu space. This is a random number, random variable. And this one is the truth. We don't get to see it, we get to see this. I could define an estimator from this posterior distribution, maybe the posterior mean or something like that, and I'd call that mu hat. Just make all the notation as extraneous as possible. And yeah, this notation gets a little bit recycled, and I think that's common. Okay, so I'm essentially telling you the likelihood from this sampling mechanism, and we've got some priors. And we'll use these priors that we've been satisfied with so far. Mu proportional to 1, and phi proportional to the inverse. I will tell you just a few things. This is kind of neat. This is equivalent to pi sigma. Say you like talking about sigma. Your induced prior would be 1 over sigma. So if I transform this into sigma space, this is the transformation result I come up with. And pi sigma squared is proportional to 1 over sigma squared. So those are all equivalent priors through transformation of this one. If I transform this one, phi space, I get that as an answer. So these are equivalent to each other, meaning they're one-to-one transformations. So all I have to do that, tell me the relationship between sigma and phi, and we know that. And then I just need to plug that thing into its PDF, the inverse transformation, I have to multiply it by the absolute value of the derivative of that inverse function. So that's transformation. So let's just keep that stuff in mind because it's pretty important. These things, scale factors, they always get multiplied by 1 over that thing. That is scale invariance. That scale factors always show up in their reciprocal form, PDFs. So remember, in a PDF, what does the Jacobian for the scale factor look like? It's that 1 over sigma that's sitting out in front of a normal distribution, or in front of a t distribution, or any scale family. And so scale invariance kind of has this sort of form versus the flat form. So these are scale invariant priors. Kind of neat. We'll talk more about it in a full lecture. And so we want to derive this thing. So all we have to do, we just need to write down our likelihood and integrate over it after multiplying through with our priors. So I'm going to write down the likelihood function. The likelihood function looks like this. 1 to n, phi to the 1/2, e to the minus phi over 2 xi minus mu squared. I'll be real specific as to where my product goes. So that's the likelihood. Phi, mu, given my data. It's IID data, so I just product across. Times my priors. So 1 over phi times 1, integrate over phi, and I'm going to do this from 0 to infinity. It's whole space that it lives in. So I'm going to marginalize it out. What am I doing? I'm averaging over that parameter. So that's what the Bayesian is giving you. They're giving you average answers. They average over things with respect to their probability distribution.
So here we're not simply doing just the product of the likelihood and the variance, we want that space mu, right?
What's that?
So usually to find the posterior, we just do the product of the likelihood of the prior. And here we're adding an integral in order to find the space mu, right?
Yeah, so I want to integrate out the uncertainty in my answer. So I don't want this joint answer and I don't want a conditional answer. I want this answer unconditioned on phi. How did we uncondition it? How did we get it out of the equation? We marginalize it. It's not just a mathematical trick. What are we doing? We're averaging across all its uncertainty. And so that's kind of a cool mechanism. So Bayesians, when you hear about optimal Bayesian solutions, they're always pertaining to problems that you want to be right on average. They can give you optimal answers with respect to their averaging method. That's what a Bayesian is commonly doing. When we get into decision theory, we'll see some other possibilities where it's like, I don't care about the average, I care about the most extreme events. And so you probably wouldn't want the Bayesian solution if you were doing that. So Bayesians are always averaging. And so I just need to simplify this. This is phi to the n over 2 minus 1. So I've absorbed my prior in there. I'm going to leave this minus 1. I always leave it. E to the minus phi sum of the xi's minus mu squared over 2. Now I have to integrate this thing. We're going to do the same thing that we did last time. We recognize this is some gamma. So which gamma is it? Been looking at gammas for a few days now, and so I always recognize the gamma by looking right there and looking right there. That's why I always leave that minus 1 wrapped up because I used it. So everything to the side of it is alpha. So this is n over 2. I usually call this alpha tilde. And beta term is sum of the xi's minus mu over 2. I usually call this beta tilde. So what's this integral? It's the inverse of the normalizing constant for gamma. So this thing is equal to gamma function alpha tilde over beta tilde alpha tilde. So those things right here. I've written down equality right here. Don't psych yourself out. We have to remember that this was always written down up to proportionality. And so as soon as I went to proportionality, while I might have equality between lines, the answer I'm looking for is still up to proportionality. And so I don't have to worry about that essentially. That's just a number. If I plug everything in, that's gamma function n over 2, and those just contain numbers. You know. And so I'm just going to write this thing is proportional to beta tilde minus alpha tilde. In our case, this is equal to sum of the xi's minus mu squared over 2 raised to the minus n over 2. So that's our posterior distribution. Look familiar? Anybody recognize it? Yeah, so this is where the conundrum comes in. It's like, okay, I've got an answer, and I can tell you that it's correct. I could also get rid of this 2 right here. That's just up to proportionality. Simplify everything. Just factorize out my constants as I go. The question is which distribution is this? And so without familiarity of your distributions, it might be a hard question to answer. The question, what dist does sum I goes from 1 to n, sum of squares, xi's minus mu squared minus n over 2 represent? Let me ask you a different question. say you wanted to do the unconditional inference, say in classical stats, and I just mean that to mean what you're familiar with from your Stat 101 classes. So old stuff, that's what classical means. So from your training before classical stats, what distribution is used to quantify uncertainties about, it's really x bar given mu in our case because we're in classical land. I want to flip that thing around. Now what people do is they do inferences on mu. They might use this distribution to do a p-value calculation. So they're looking at more extreme x bars given a hypothesized mu naught, or they might build a confidence interval out of this distribution and do a pivot. Those are their strategies to inferring about mu. But they're going to have some distribution modeling x bar given mu. And you don't get to know sigma squared. So what I'm just saying right here is I'm not telling you what sigma squared is. So without knowledge of sigma squared. Not all at once. Keep it down, you guys.
T.
It's okay, Sierra. I see you cracking your knuckles back there.
I didn't crack up that time. That was my back.
Feel you. So they do something different in your Stat 101 class, and presumably you've touched statistics before. What distribution do people use to talk about mu, or do some sort of proxy form of inferring about mu, given you get to see all the xi's, and it turns out x bar is sufficient for those, maybe.
T.
What's that?
T.
T. Thank you. So, not normal, T. So you move from the Z table to the T table. Is this brand new? Embarrassing, right, Andy? So, we all need a reminder. So the answer is a T distribution. T distributions. Let me go back to this. What distribution do you think is represented here?
T.
It's a T. So that is the correct answer. If n is bigger than 1, then it's T. Okay? Otherwise, it's going to be some sort of improper thing. So it'd be the same answer that we got before. So it turns out the answer is T. Let's show it. But I probably need to show you what a T looks like. You guys know what T's look like? Who knows what a T density looks like? Who does not know what a T density looks like? So quite a few of you. Yeah, isn't it kind of funny? I remember going to a stats professor when I was an undergrad, and I'm like, we're always talking about T's, what do they look like? And he had to grab a table to pull it out and show me. All Bayesians would be able to just pull this out. We're always writing these things down. So again, one of the keys to being successful in this class is knowing all your distributions. So know all the exponential family distributions. We use them a lot in this class. And ask yourself the question, do I know what that distribution looks like? So the quicker you can get into just writing these limiting distributions down that come up all the time, the quicker you'll be an expert at Bayes. So T distributions look like this. So I'll say T densities look like, and I'll say Z, I'll write this down as PZ given some parameters. So there's 3 parameters that underline a T. That's one more than a normal. So I'll write it down as mu, S, and nu. So those are very typical parameters that people will use. So this is called the center. Sometimes it's a mean, and sometimes it's not a mean. We'll talk about the variance of this. So if n is big, it's mean. So how big? Bigger than 2. So it's mean. This is a scale. Sometimes people will call it a standard deviation. S squared might be the variance term, but that would be your scale term. If n is bigger than, if you have 3 data points, then that scale is a standard deviation. It's called the degrees of freedom. So what does it look like? It looks like this. This is the part you need to know. 1 plus z minus mu squared nu s squared to the minus nu plus 1 over 2. This is a little bit more angle to nu, the degree of freedom. So degree of freedom plus 1. Turns out there's a multivariate form of it, and instead of just squaring this thing, we would have the quadratic form where we have maybe a covariance, but a scale matrix shoved up in between the quadratic form. And it turns out this plus 1 would change to plus the dimensionality of the problem that we're working at. We'll look at that in a week or so. So we'll be doing T regressions and Cauchy regressions and all kinds of different regressions in this class. Change the error form from that normal assumption that we're always using. Okay, so if you wanted to know what the normalizing constant is, I think I know it. I think it looks like this. Square root nu pi s. That's what it looks like, whatever. So, might help you to recognize that limit is n goes to infinity 1 plus x over n raised to the n. So this has the same asymptotics as this. So if I just take this limit right here, this is ex, wonderful mathematical fact. And so this thing right here, as the degree of freedom goes up in the problem, it starts to look more and more like a normal distribution. That's kind of a cool thing. Okay. Let's go back to the problem at hand. It's not at all clear that this thing right here looks like that thing. But with a little bit of algebra, we can make it look just like it. So here's what I want you to remember. The inverse normalizing constant to a gamma looks like a t distribution. So that's what we just did, right? How do we get this thing? It's the inverse normalizing constant from a gamma. That's what we did in the integral, and those have the forms of t's. It's a really neat thing. So back to the problem at hand. Pi mu, given x, proportional to sum of squared errors, xi's minus mu, squared minus n over 2. That's going to be sum. I goes from 1 to n. I'll be explicit about my braces right here. This I'm going to expand. Here's what I'm going to do first. Is I'm going to shove a minus x bar in here, and I'm going to shove a plus x bar. So I'm going to add x bar, and I'm going to subtract x bar. How do I know to do this? Every time I see these little polynomials that are surrounded, xi's are flanked with mu, I always know that that answer is going to be centered at x bar. How do I know that? I guess from what I'm about to show you. And it happens like that every single time. And every time I see these forms and I shove x bar in there, all the math works out beautifully. So, why? Because when I square things, the cross terms cancel out. And so you'll see that. So, I remember being in graduate school and people asking, how did you know how to do that? And that was a good question. And I think the answer really was because you've done it once, beautiful things happen, and it's mathematics. rules don't change over time. And so look what happens. Xi minus x bar, so I'm just going to write it like this, plus x bar minus mu. Square that thing out. So really explicit with the braces here. And so now I'm going to expand that square. I goes from 1 to n. I have a big power going on. I'm going to be explicit with my sum right here. Xi minus x bar squared minus, there's a plus, sorry, this is plus. Xi's minus x bar minus mu. There's two of those things in both directions, plus x bar minus mu squared. Try to remember what a t looks like. Keep it up here. This is what we're aiming at. 1 plus c minus mu over s squared mu minus mu plus 1 over 2. This is just a reminder of the form we're aiming at. So I'm going to drag the sum across all of these terms right here. And so what I'm going to get is my answer, sum of the xi's minus x bar squared. So the sum is just affecting this term. So I'm going to slide my sum across, plus 2 times the sum xi's minus x bar minus mu, plus sum x bar minus mu squared. And all of this is raised to the minus n over 2. Here's what I was saying before. I can take this thing, I can pull that out. It has nothing to do with the index of the sum. And when I sum xi and I subtract off x bar is becoming nx bar, and the sum of the xi's is nx bar. So this term is 0, right here. 0. So that's why we always expand around x bar. So when you see that and something is squared, expand around x bar and you will kill the cross term. And so this thing is just sum of the xi's minus x bar squared plus this thing right here, sum of this constant term. So that's going to be nx bar minus mu squared minus n over 2. So that's our answer. It's starting to look more like this. There's 2 terms, they're being added together. But I want the leading term to be 1. And so how do I do that? Well, notice this doesn't have anything to do with mu over here. Mu is right here in the equation. And it's kind of nice, what we notice is that this equation, at least as a function of x bar, is centered at mu, or mu is centered at x bar, depending on how you want to look at it.
So on the inside, you can just divide out by xi minus x bar squared and you get something proportional.
Thank you, Ben. So Ben has given me permission to do this. So he's going to divide everything by this. What he's doing is he's going to multiply and divide by it simultaneously. So divide by something, call that A, and I'm going to multiply by that something. I haven't changed its form, but I'm going to do it all the way across this whole thing. What I'm going to do is I'm going to factorize out that par I'm pre-multiplying by. And that's just a constant because it didn't have anything to do with mu. And so let me just do this once very detailed. So I'm going to write down sum of the xi's minus x bar squared plus n x bar minus mu squared. What I'm going to do is I'm going to divide the whole equation by sum of the xi's minus x bar squared, and I'm going to multiply it all by that. And then I'm going to raise it to the minus n over 2. So sum of the xi's minus x bar squared. So same term on both the numerator and the denominator. But this term right here I can now factorize outside. So this is going to be sum of the xi's minus x bar squared, raised to the minus n over 2. So a lot of explanation for something I'm throwing away. So I won't explain it in that great of detail next time. But this part I can get rid of and just write this thing as up to proportionality. That's kind of a nice thing. So this thing is equal to 1 plus n x bar minus mu squared divided by sum of the xi's minus x bar squared. That goes from 1 to n. Minus n over 2. So I've got the 1 in there. So it's just up to proportionality, what we're doing. It's kind of a nice thing. When we do this in the multivariate case, you're going to need a matrix identity to do this. Okay? So it comes from the Sherman-Morrison formula for determinants. So just be aware of that in a couple weeks in a future homework that you don't yet have. You will be needing a matrix identity when you get to this step. You're going to need to change everything from matrix form into scalar form. And it's a really cool formula for that. And so I'm almost ready to recognize all the terms. Just keep in mind, what we usually use is a scale estimator. So we usually do something like this. S squared hat is equal sum of the xi's minus x bar squared divided by n minus 1. This is a typical scale estimator. It's the unbiased one. So I see something that looks like that right here. I'm going to replace its name. So I'm going to rewrite this as 1 plus, I'm going to flip this thing around. I like my random variable always to lead. Squared, this is going to look like s hat squared divided by n, but this is multiplied by n minus 1, right here. So to get the s hat squared, I have to divide this by n minus 1 and also multiply by n minus 1. And so minus, I've got n over 2. If we go back to our form that we're aiming for, I've got the scale right here. Here's the scale. Everything. That looks like a pretty convincing scale. This is estimating sigma squared. And how much uncertainty do I have in the whole system? It gets divided out by n, just like normal distributions do. And here's my degree of freedom, n minus 1, it looks like. But I don't have that degree of freedom up here. I need that here. I'm off. So I'm just going to force it in. Minus 1 plus 1. So this now is the degree of freedom, which matches that. This is the scale. And this right here is the center. So it's just algebra. So practice that problem. I'll probably ask you to do it soon. That's what t-distributions look like. So our answer for the Bayesian, after all this work, you might think, geez, I'm not getting a lot for my money because I keep getting the same answers as the classical guy. Let's talk about it for a second. Here's my posterior distribution. My mu, given x, is a t. It has center x bar, scale s hat, squared over n. Just to keep it all consistent, let's take the square root of it. the notation I used before, and it has degrees of freedom n minus 1. We lose a degree of freedom because we're having to do this estimation right here. When we do this to approximate the center, we threw in x bar to do it, and we lose that degree of freedom. That's the interpretation we get in a Stat 101 class, and we have the same thing here. So what's different about this from the classical answer is this is a distribution on mu. It's not on x bar, like the classicist will use it. And so I can construct my intervals, that tell me where I believe mu is, and it also covers very nicely too. If I ended up doing a simulation study, I'd notice that I cover very well. We'd also notice that my credible intervals that I would get off of this are going to be the same confidence intervals that a classicist would get. They would have completely different interpretations. The reason being is simply because of the symmetry in x bar in mu. We used a flat prior on it. And so I can just, instead of pivoting, I upgrade my random variable to I upgrade my unknown to a random variable. That's the fiducial thing. How did I do it? I used Bayesian's theorem to do it. So same intervals, same coverage, same distribution, but where we'll differ if we start hypothesis testing in all of this. We do the two-tailed test, the Bayesian and the classicist, or some form of frequent test will collide. We'll talk about that soon. So this should give you at least some confidence that everything you've done in all of those papers where you use t-distributions and normal distributions, that if you were to operate as Bayesian under marginal reference priors, we would have had the same inferences. So Bayesians still do the same sort of thing, but we do something different with this distribution. I just gave you the way as Bayesian to derive it. If you were to derive a t-distribution from a scale mixture of a normal with a chi-squared, transforming appropriately, so you have the normal 0, 1 divided by square root of the chi-squared divided by its degrees of freedom. If you're trying to figure out what distribution that is, you would solve the exact same integral that we just solved. So you have to do that same integration. So it's not a coincidence that we get the same answers. So let's talk about something different in a moment.
It's just the same because of the symmetry between x bar and mu, and weighting everything. So if the prior was not 1, then
we would have had a different answer. So we also have mechanisms as a Bayesian if you wanted to inject information. So long as you did it in a judicious way, you'd have a mechanism to change your answer. Yeah.
What does degree of freedom mean?
So a lot of different interpretations, but it's a parameter in the model. Think of it that way. The degree of freedom doesn't even have to be an integer, like we're used to seeing. In this case, it has the interpretation, it's going to be an integer. But it's a parameter in the model, and what it does is, in a normal distribution, we have variance, and it pushes things around, spreads things out. What the degree of freedom actually does is it lifts the tails up and down. It puts more mass under the tails. And so it's a mechanism for weighting the tail behavior. So a normal is exponential decay, squared exponential decay. And so maybe you want more mass. Turns out when n is equal to 1 in all of this, you did this analysis, or sorry, the degree of freedom was 1. So that means you have 2 data points, n is 2. This is a Cauchy distribution, and those have wildly heavy tails. I want you to experience that, so in future homeworks, I'm going to have you play around with this model a lot. You'll see what the degree of freedom is doing. Some interpretations of it are how many data points did I need to use to estimate the variance of the model. You might say, well, I need n of them to do the xi minus the center, but I also had to recycle all of those data points to estimate the mean. So I have to estimate the mean as well, so I lose a degree of freedom in it. So there's these sort of interpretations as well. They're equally as valid. But I think it's a description of what it does to the model is it lifts the tails up and down without just spreading the whole distribution out. Make sense? Good question. You'll get a feel for it. Those big heavy tails can be used as a modeling mechanism. So I like using heavy tails for things. I want to show you something new. We'll motivate for a second. So this is a new problem. problem. And there's a lot of words that people use for this. I'll call it prediction. But some people like to call it forecasting. Okay. And so there's a Bayesian way to do all of this. Up until now, we've kind of studied in a couple examples how to do parameter estimation. This is a different problem. So I want to infer about the future, something I haven't seen. So let's say I have data. It comes from some model. I'll write it down, fx given theta. It's just generic notation. And I'm going to make it real easy, although we don't have to do this. We'll go over the IID case and the non-IID case as well. But for now, let's just say everything's IID. And I want to predict about something I haven't seen. So I have n of those, and we want to know to predict a future observation. And I'll call it x tilde. I'll call that a future distribution. Let me just ask a basic question. If this is all IID, can I use the past to predict the future? No. So we have one saying you can't do anything. If everything's IID, this simple mathematical form that we always play around with, can we use it to predict the future? We have answered no. So don't even look at previous data. It won't help you.
So condition on the parameter if you can't.
That's right. So there's a big difference on this. And so if I gave you theta, seeing x's wouldn't help you to tell me a new x. But what I can do is I can use all those x's to try to help me learn what this distribution is. If I did give you this distribution and knowledge of theta, the old x's can't help you. That's true. However, what are we actually doing is we're trying to learn the model uncertainty, and in the way that I'm writing it down, we don't know theta. So what we're actually doing with previous data is learning about the parameter space. If there is temporal correlation between things, then you have even more information. So we're going to come back to this problem next time and study how a Bayesian actually does it. And I'm going to give you a generic recipe, and it always works. And here's kind of a bonus that if you've got a computer, it's usually easier to figure out stuff about this distribution than it is about the posterior distribution on the parameter space. And I'll show you why soon. It's really very cool. So more on that later. I'm going to hand back your homeworks as well. So one